Hello, my name is Dan Harmon, and I am the Automotive Sector Marketing Engineer for Texas Instruments' current and magnetic sensing product line. In this video, I will discuss how the magnetic field for a permanent magnet changes over temperature and how TI's Hall effect sensors compensate for this change. The residual magnetism or remnants of a permanent magnet is an indication of the magnetic flux density of the magnet and is denoted by the letters BR. The remnants of a permanent magnet will change based on the temperature. This change is often defined as a negative temperature coefficient or as a positive reversible temperature coefficient in terms of either Br% per degree F or Br% per degree C. This chart excerpt shows the remnants and reversible temperature coefficients for some common magnet types. The highlighted magnets are used as examples in this video. This plot shows the change in remnants for the magnets referenced on the previous slide over the temperature range of -50 degrees C to +150 degrees C. Note that in general, the remnants of a magnet decreases as temperature increases. Since remnants for a permanent magnet changes over temperature, the magnetic field of that magnet will also change. This plot shows the magnetic field strength for the example magnet described on the left at a few different temperatures. Note that the impact due to temperature is larger closer to the magnet because the change in remnant is a percentage and not an offset. TI's linear Hall effect sensors are designed to adjust sensitivity automatically to compensate for the remnants change in magnets. As shown in section 6.6 of the DRV 5055 datasheet, this compensation is done in percent per degree C. This plot shows an example of how the sensitivity of the DRV 5055 adjusts over temperature. In a system, if the Hall devices are not compensated, then the output voltage would decrease as temperature increases due to the decrease in remnants of the magnet. Without sensitivity compensation, the magnet would then need to be moved closer to the sensor to get the same output voltage. On the other hand, if the magnet does not drift with temperature or only drifts slightly, then the sensitivity compensation will cause the output voltage to be higher than expected as temperature rises. These plots show the change in remnants over temperature for an N38 and ceramic 5 magnet. For the N38 magnet, the temperature compensation in TI's Hall sensors is designed to be the inverse of the change in remnants of most magnets of this type, enabling Vout to stay relatively constant over temperature. As can be seen, the ceramic 5 magnet on the right has a more significant change over temperature than the N38 magnet. The Hall sensor temperature compensation is not inversely matched to this type of magnet. So Vout will not stay constant over temperature. The temperature compensation for this and other non-neodymium magnets may need to be done manually through calibration depending on system requirements. To find more magnetic position sensing technical resources and search products, visit ti.com/Hall effect.